I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this class and just help us to, again, Lord, just to glorify you in whatever we do, Lord. In your name I pray. Amen. All right, so last time I introduced the concept of an integral vector field, integral curve to a vector field, right? And so this class I want to talk about conservative vector fields and also probably exact equations. We'll see how that happens. So I want to talk about conservative vector fields. A little bit about physics, and hopefully something about exact equations. All right, so first of all, one of the things that I think many times in many versions of Calculus 3 doesn't get nearly enough attention is the idea of a conservative vector field. What is a conservative vector field? Definition. F, let's say it has a domain U, which is a subset of Rn, all right? And I guess it's mapping to Rn is a way we could look at that. Is a conservative vector field. Actually, instead of putting this U here, let me just say Rn. I know I got to do. I'm sorry, guys. Choices. Is a conservative vector field on U, all right? If there exists a potential function little f such that big F is equal to the gradient of little f on U. All right? Now, primarily, of course, in Calculus 3, we're interested in the case n equals to 2 or n equals to 3, right? Maybe in calculus, if you're lucky, maybe in calculus 2, you might have even thought about n equals to 1. We talk about n equals to 1 a lot in physics. That's the one-dimensional case, right? Let's see here. So let me just give an example maybe to get started here. If I have f, and I'll keep it two-dimensional for the moment being, but if I have fx comma y equal to, I don't know, how about x plus xy, and then y squared, and let's see here. Put something there, trying to think. Maybe xy works. I'm trying to think here. The question is this the gradient of some function? Question mark. So how do you find that function? What do you have to solve? You have to solve partial f partial x equal to x plus xy, right? And you have to solve partial f partial y equal to y squared plus xy. You got to do those both at once, right? So a common technique to do it, if you can't just guess, is to integrate both of these one at a time, right? So if I integrate the first one, that suggests that f is equal to 1/2 x squared plus 1/2 x squared y plus c1, which is a function of y. And if I integrate, so integrate basically with respect to x, integrate with respect to y, holding x fixed. Down here, we get f is 1/3 y cubed plus, uh-oh, I think I might have gotten into trouble. Trouble. All right, I need to fix the original function if you don't mind, so you'll forgive me. This was supposed to be xy squared, and this was supposed to be x squared y. As usual, I caution you, you're not allowed to do this on tests. Like once you get your terminal degree in mathematics, like part of your ceremony of becoming a doctor, they say now you are allowed to change problems. It's like it's part of my my authority as having a doctorate in math. Yeah. So, I'm just kidding. Do I need to say I'm kidding? I don't think I need to say I'm kidding in here. I think you guys probably get it. Let's see here. So integrating that, I get 1/2 x squared y squared was the point. And integrating this, I also get 1/2 x squared y squared with my fix plus c2 of x, right? So you can compare both of these, and then you can read off what the potential function is, right? What's the potential function here? Apparently, I need to remember not to use that green marker. It won't show up. 1/2, I need a 1/2 x squared. Oh, this is worthless. Plus a 1/3 y cubed, right? And then what else? A 1/2 x squared y squared. And that'll do it, right? You could add a constant if you like, but what I just wrote in red is a potential function for this vector field. Right? You can see that if you, well, maybe you could see it. I can't quite see it. Oh well, I tried. If you take the gradient of that function, you get back the vector field, right? Which shows you, by definition, it's conservative. Where is it conservative? On what domain? You're like, you had this u up here, and on u, and on u. You've written it 3 different times in this definition. What's u here? What's the domain? By default, when we work problems in this kind of course, the domain is always taken to be as large a set as possible, right? So what's the largest set possible on which this makes sense? And by the way, sometimes that principle gets you into trouble. Sometimes you really do need to say explicitly what the domain is, because the issue is very much tied to the domain. Not talking about what the domain is in question obscures the actual problem. But here that's not the case. Here the domain is just all of R2. All right, these are polynomial expressions. They're smooth everywhere. So in fact, this is a conservative vector field. Now what does that mean? If this is a force field, if this is actually the force acting on an actual physical particle, what does that tell you? Why do we call it a conservative field? If that's the net force. Do you remember what we derived? Maybe not. Let's work through it. If if F is equal to the net force on M, then what's Newton's law say? Newton's second law says that F is equal to the mass times the acceleration, right? But what is the mass times the acceleration? That's also mass times the change in velocity dv dt, like so, right? So we can consider two events, right? Event 1, event 2. And if we have two events, and this is the net force that's acting on the particle between these two events, we can calculate the work done by the force on the path that goes between these two events, right? What's the work done? Remember, we define the line integral in calculus 3 specifically to calculate the work done on a particle by a force which is varying with position and also direction, right? I mean, so the whole point of the line integral is to calculate work done by a vector field. So this is actually going to be the integral of f dot dr, right? That's the work done. But we can do better than that. If we write that out explicitly, what was the definition of this integral? This is, by definition, the integral from, say, time 1 to time 2, right? We take the vector field, we evaluate the vector field at the position, right? And then we take the dot product with dr dt, and then we integrate over t. That's the definition of the line integral, right? Now, the thing I'm about to put in red parentheses, we could say more about that physically, right? What are we integrating? To calculate the work done, we're actually integrating the power developed by the force over the path. See, because that's f dot v, and f dot v is power. So the integral of the power over time gives you the work done by the force. But anyway, let's use Newton's law, right? Well, not quite yet. Well, yes. I mean, fine. I'm going to run out of board space here pretty soon. The point is that this is also ma, right? And this is v. See, so since this is the net force, we can apply Newton's law, second law, and we get that this is the integral from t1 to t2 of what? Of m dv dt dotted with v dt. Then, there's a neat little trick that we can do here. An identity involving calculus and the dot product says, you know what, this is really just the integral from t1 to t2 of d dt of 1/2 m v dot v. Because if you take the derivative, how does this work? Did you guys understand that step? If we go this way, what's d dt of v dot v? This is dv dt dot v plus v dot dv dt by the product rule for the dot product. So of course that's 2 v dot dv dt. And so that's why that step makes sense. And there's where the half came from, because we're taking the derivative of the dot product of the velocity with the acceleration. Taking the derivative of the dot product of the velocity with itself, which then gives us 1/2 the dot product of the velocity with acceleration. But then, the net change theorem, we have the integral of a total derivative, so what's the answer? This is, and of course, what is v dot v? It's just v squared, right? Speed squared. So this is 1/2 m v squared evaluated from time 1 to time 2, which of course we would usually write as kinetic energy 2 minus kinetic energy 1. This is the so-called, what's this theorem called that we just derived? In physics we call this the work energy theorem, right? It says the change in the kinetic energy is equal to the work done by the net force. This is true for any net force acting on a mass, constant mass. I mean, mass had to be constant here. I did not assume that F was conservative, did I? No, I did not. Now, if F is conservative, right? And F is equal to the gradient of the potential little f, then the work done, we can calculate a different way, right? On m by f is what? The integral over, and I forgot something. This integral doesn't make sense unless I put the curve here, right? It's the integral over that curve. That's why I labeled it C. So it's the integral over the same curve of f dot dr. All right, so I'm just, all right, fine. But what is that? That's the integral over C of the gradient of f, right, dot dr. Now, to make this discussion better, I should really label the initial and final points of this curve, right? Let's label them like, I don't know, how about this is, I suppose this is r of t1, and this is r of t2, right? So we could call this point 1, we could call this point 2, just to give them easier names, right? And so what does the fundamental theorem of calculus for line integrals say? It says that this is equal to f of p2 minus f of p1. This is FTC for line integrals. Because remember, our curve goes from p1 to p2, right? And if we take the line integral of a gradient, it's just the difference of the gradient. Difference of the function being gradiented. Gradiented? I guess that's not actually a word. Do you guys understand the words coming out of my mouth? Yes? Okay, good. Now that would be equal to, so this, apparently, this is equal to what? Kinetic energy 2 minus kinetic energy 1, right? And so what do we get? This implies that kinetic energy 2, let's see here. Minus f of p2, right, is equal to kinetic energy 1 minus f of p1, which you all recognize as conservation of energy, right? I'm joking. You just shouldn't recognize that as conservation of energy, because you're not like, yeah, I remember conservation of energy says that the kinetic energy minus the potential energy is constant. Did we say that? We did not say that. It's kinetic energy plus potential energy, which is constant. So how do physicists make that plus appear? What do they do? What's the difference between their potential function and the potential function little f I did today? Right. So physicists say that f is equal to minus the gradient of u, where u is the potential, u is potential energy. And so basically, in summary, just set f equals to minus u, and then this becomes, you know, u2, rather, this becomes, let's say, k2 plus u2 equals to k1 plus u1, which is, of course, energy 2 is equal to energy 1. Energy is conserved. Yay, it's a conservative force, right? So if you're thinking about potentials in physics, you got to put this minus in, because otherwise it's not potential energy, it's something else. Which direction does the gradient point we talked about last time for the level? Remember, for the level curve, the gradient points in the direction that you level up, right? So if f is equal to the gradient of f, that means that the force produces motion in which f is increasing, right? Does the conservative force push particles towards directions where the potential energy is higher? No, you learn the opposite, right? Nature tries to minimize potential energy, right? So that's what part of the minus is coupled to that idea as well. If we want forces to produce motion towards lowering potential energy, then we need that minus there as well. All right, anyway. So work energy theorem, that's the significance of, that's why we call it a conservative force, right? All right, great. What, yes?
Basically that means the path of the curve doesn't really matter.
Yeah, that is true. So that, very good question. So the path of the curve doesn't matter. So my next question for you would be, what are the ways we can characterize a conservative force? Right? What are the equivalent ways of looking at a conservative force? So I gave you the definition. I gave you its significance to physics, right? Classical mechanics. My definition is in n dimensions. I'm really just thinking about 3 dimensions for this. Actually, this derivation is not 3-dimensional, is it? There's nothing particularly 2 or 3-dimensional about this derivation. If you look at it, I didn't use 2 or 3 dimensions. This is actually true in n dimensions, this theorem. But anyway, this is a theorem. The following are equivalent. Following are equivalent. 1, F is conservative on U. And here I mean F is equal to the gradient of some little potential function F. That's our definition, all right? 2, if here's my picture of U, all right? If we have any 2 paths, C1 and C2, and they have common, like, terminal points, right? So 2 paths that start and stop at the same points, then what can we say about the conservative force? The integral of F dot dr is equal to the integral of F dot dr, right? Over C1 over C2. We had a name for this. What's this called? What property of the vector field is this? If the work done by the vector field is the same no matter which path you travel between 2 points, what is that? Yes, path independence. This is path independence. So path independence. Closely tied to that is that the integral around any loop is what? So here's a picture of a loop. Right, 0. Now, to be clear, though, I'm not being super clear about the qualifiers here. I mean, quantifiers. I mean for all possible paths in U. All right? It's not enough that it just happens for one pair. Like, it has to happen for all possible paths. That's path independence. It has to happen for all possible loops inside U. All right? That's what I mean by 3. Okay? Some people will put like a little circle here to indicate that it's a closed path, by the way. That's what that notation means. And if you look, sometimes they'll put like a little arrow to tell you whether it's a clockwise or a counterclockwise path. 4. Let's see here. What else is there? And then 4, it gets technical. 4, and this is for n equals to 3. For n equals to 3 and more fine print, U simply connected. The curl of F equals to 0. Or, for n equals to 2, and U simply connected, let's see, what's the two-dimensional curl? It's essentially that partial q partial x minus partial p partial y equals to 0. That's the z component of the curl if your vector field is PQR. Now, if U is not simply connected, it's possible to have the curl be 0 or to have partial Q partial X equal to partial P partial Y. And here, by the way, so that this is less ambiguous, I'm saying F is PQ, right? That's what I mean by P and Q there. Now, if you drop that condition of simply connected, all right, it's possible to have vector fields which have curl 0 or meet this condition, partial Q partial X equals partial P partial Y, and yet are not conservative because of like topological defects in the domain. I'll show you an explicit example, all right? If you haven't seen that before, okay, it's okay. So the proof, I mean, I proved these are equivalent in my calculus 3. You may or may not have seen any of that. I don't know. I think it's useful, though, to see the connection of Stokes' theorem and number 3. All right, so let's look at that. Suppose, so I'm not going to prove all of it, obviously. I mean, that's not really what we're here for. But I want to make some connections with Green's theorems and Green's theorem and Stokes' theorem here, so you see a little bit of the connection between this material. All right, so suppose that F has curl of F equals to 0 on U, which is simply connected. So I'm thinking three-dimensionally for the moment. And I'm just going to envision U like a box. What does it mean for it not to be? What does simple connected mean for a domain? All right. Well, if you could imagine that there was a pole in the middle of this room that went from the floor all the way to the ceiling, all right? Then this room wouldn't be simply connected in the sense that if I put a loop around that pole, there's no way I can pull that loop past the pole without getting over it or under it, right? But I can't because it's all the way to the edge of the space. So if there's some obstruction in the space which prevents you from contracting loops to a point, that signifies a lack of simple connectedness. So for example, if you take all of 3 dimensions and you eliminate the z-axis, then that space is not simply connected because you can't move loops past the z-axis, which is missing. All right. In 2 dimensions, something being simply connected means that, again, you can't contract loops to a point. So if we take like the plane and remove a point, the so-called punctured plane, this is not simply connected because there's that point missing. This is the fine print that's needed to apply Stokes' theorem and Green's theorem. You need simple connectedness of your space. Now, what does that have to do with what we're doing? So if U is simply connected, think about this. Then you could put a surface, right? Well, first of all, take any loop, pick any loop in here, right? So imagine a loop, it's inside U, right? If U is simply connected, if you think about it in your mind's eye, you should be able to see that you could draw a surface which takes the loop as its boundary, right? Can you see that? If it was simply connected, you should be able to shade this loop in. There's not just one way to do it, right? Not just one way to do it. Lots of different ways. But we could shade this surface in, this loop in, and we could call that S for surface. And we could say that the loop is the boundary of that surface, right? Yes, sir?
Multiple times you emphasized that the obstruction had to go from the edge of the surface to the other edges, or the space.
Yeah.
If there's an obstruction that doesn't completely go,
If there's a way to get
the pole wasn't all the way to the ceiling.
right, then you could slide the loop up over the pole, and it would still be simply connected. Yeah, I think so.
Okay.
I think that's the case. But I will admit, trying to describe precisely what simple connectedness is without a proper discussion of topology is challenging. I just know it when I see it. I mean, our typical examples of things that are not simply connected is pretty much the punctured plane. Well, I should stop there for the moment. So if we think about this loop, right? My goal is to what? What I'm trying to do here, guys, is I'm trying to prove that 4 implies 3. I'm assuming 4 is given. I'm trying to show that 3 holds. Right? It's relatively simple to show that 3 implies 2, because you can always take a loop and divide it up into a pair of paths. And then the property of the line integral says that 2 and 3 are equivalent. And that's not hard. I mean, to show 2 and 3 are equivalent, all you have to really do is look at this picture and go, hey, that's a loop, right? But the loop is what? It's like C1 union with minus C2, right? So you can always take a pair of paths with common terminal points and view it as a loop. And conversely, you can always take a loop and divide it up into a pair of paths with common terminal points. And if you look at it, you can prove that 2 is equivalent to 3 in view of the properties of the line integral. All right. So anyway, I'm trying to get back to 3 from 4. So I'm thinking about this loop. I found a surface, which is the boundary of that. And now I'm going to apply Stokes' theorem. What did Stokes' theorem say? Do you guys remember? It says that the integral, the surface integral, right? Maybe you write 2 integrals there. Surface integral of f, right? Dot ds. Oh, man. No, that's not it. Oi, oi, oi. Sadness. Sad. Hey, wait a minute. You guys took the course. You tell me what Stokes' theorem says. I just taught it. Why should I know? No, Stokes' theorem said that the flux of the curl is equal to the line integral of the vector field around the edge. So I had my ducks out of order here. So it's the surface integral of the curl, right? The flux of the curl there is equal to the integral over the boundary of the vector field. Now this assumes that S is a simply connected surface. What's a simply connected surface? Again, a simply connected surface is one where, I mean, if I draw a picture, if this is my surface, I can take a loop, right? And I can take any loop and I can shrink it, I can smoothly deform it to a point. If I can do that for all possible loops, then it's simply connected. If I had a hole in my surface, if this was a hole, then if I took a loop like this, right, and I could try to deform it, right, but then I would eventually get stuck on that hole, and so that surface would not be simply connected. But you could take that surface and cut it in 2, and if you cut it in 2, then those 2 pieces would be simply connected, right? All you'd have to do would be just to take the surface and cut it like this and like that. Then this upper half is simply connected and the lower half is simply connected. So you can play that game. All right, anyway. Stokes' theorem. We're assuming that the curl is 0, so what does this give us? So there you have it. Stokes' theorem is what implies that the integral around a loop is 0, given that the curl is 0. What's the 2-dimensional analog to this? That actually has more to do with our course. All right. How about 2 dimensions? So we're thinking about f equals to p comma q, right? With, what are we going to assume? We're going to assume partial q, partial x, equals to partial p, partial y, right? That's the same as partial q, partial x, minus partial p, partial y, which, by the way, is the z component of the curl of PQ0. Incidentally, side remark, saying that partial q, partial x minus partial p, partial y equal to 0 is to say that the z component of the curl of PQ0 is 0. All right. So suppose that this is true on simply connected U, which is a subset of R2, right? Then what theorem comes to bear? What's the two-dimensional analog of Stokes' theorem? This you probably covered in Calculus 3 a little bit more carefully because it wasn't right at the end of the semester. It's not the red theorem, it's Green's theorem. Sorry, I'm an idiot. So Green's theorem says that the integral along a, well, let's say I'll say a region R, right, of partial q, partial x minus partial p, partial y, right, dx dy, or let's say dA, that's equal to the integral over the boundary, counterclockwise oriented, right, of p dx plus q dy, right, Green's theorem. Right? Remember that? Let me remind you the picture here. This could be R, and what's the boundary of R look like? It's counterclockwise oriented, right? And I'm assuming R has no holes, right? If there is a hole, then I have to use Green's theorem for an annulus, but that's another matter, all right? So what happens, you see, I mean, I think you see where I'm going with this. If partial q, partial x is equal to partial p, partial y, what do we get? We get the integral of p dx plus q dy equals to 0, right? And so thinking about this more completely, here's my set U on which we're given that, you know, partial xq equals to partial yp. It's true everywhere in there, right? So I can take any loop in here, right? And I can think of it being counterclockwise oriented, and I can fill in the loop. And then I can apply Green's theorem, and I get that the integral of p dx plus q dy is 0, right? Which says what? What does that mean? That means if partial p, partial y is equal to partial q, partial x, I can't make up my mind which order to write it in, I'm sorry, but potato, potato, I guess. If this on simply connected U subset of R2, then there exists f such that the gradient of f equals to what? I mean, p comma q is a conservative vector field. So gradient of f, p comma q is what I'm getting at here. Any questions about this? I think a natural question to ask is, what, if anything, does this have to do with differential equations in the plane? Right? What's the connection between what you're saying right now and our study of differential equations? What's that? Calc 3 review. That is true, but I'm not just reviewing everything in Calc 3. There's a preachy underlying message here. I think so, and also just some things I like to say. In retrospect, it'll become obvious which parts I was misbehaving. I mean, work energy theorem is probably an example of that. Maybe not, though. We do talk about, there's a thing later we call the energy method, which is actually based on that. But I think I can erase this, yeah? Maybe I shouldn't, though. I think I can. So let's talk about, I'm going to come back to this, all right? Let me just finish this thought before I go on. So here's a theorem. Let's just rewrite this theorem in a different notation. I think it'll make it really obvious what that theorem tells us, which is that the integral along a loop, right, of p dx plus q dy is equal to 0, provided what? What condition do we need to make that happen? I'm sorry, I'm writing this kind of out of order, right? I'm writing the result here, and what's necessary over here. That's bad math in some sense, right? Would you like me to reverse it? It's fine. Okay. Thank you. How about provided that partial q, partial x is equal to partial p, partial y on some simply connected domain of R2, which contains what? The loop. But it's more than that, right? It's a little bit more than that, because it also says that there exists f such that what? Such that df is what? It's partial f, partial x, dx plus partial f, partial y, dy. That's the total differential we talked about. But what is partial f, partial x? I mean, it's the potential function, right? So that would be by p dx plus q dy. All right, so let's thought process, all right? Number one, we're given, suppose we're given p dx plus q dy, right, equal to 0. Step two, if we have this, if we can meet the condition partial q, partial x is equal to partial p, partial y on simply connected subset of R2, then what? Then there exists f such that what? Such that df is equal to p dx plus q dy, right? So what does step 3 say then? So step 3, so let me say that this is star, all right? This is a given differential equation in what's called Pfaffian form. I'm going to explain more what I mean by that in a minute. I need to connect with the theorem while we've got it on the board, okay? So if we have a differential equation in Pfaffian form and it satisfies this condition on a simply connected set, then that implies that there exists a potential function, p dx plus q dy. And so what does star actually become? We just have what? df equals to 0. That's star. How do you solve df equal to 0? What's the solution? What's that say about f? Doesn't exist. No. That's right. That says f is a constant. That's the solution to that. Right. More to the point, though, what I'm about to box here, this is the solution to star. Let me put it in words, just to get to the point. If you can take your differential equation in Pfaffian form and rewrite it as the total differential of a function of two variables, then that function of two variables has level curves which are solutions to your differential equation. Such a differential equation is called an exact equation. To test if an equation is an exact equation or not, we need to check the condition. Does partial q partial x equal to partial p partial y? Now in textbooks and differential equations, they usually use m and n. So if you have f equal to m comma n instead of pq, then we have m dx plus n dy equals to 0 is exact if and only if partial m partial y equals to partial n partial x on the domain of definition for the differential equation. What's the domain of definition for the differential equation? The largest set on which the formula given makes sense is the default, unless someone says otherwise. Just like that game we played in Calculus 1. Tell me the domain of this function, right? And then your job was to say, it's got a natural log of x, so I need x positive. It's got division by x squared minus 9, so x can't be plus or minus 3, blah, 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 blah. All right. Ooh, well. Let's see here. Where were we? All right, so based on my first example, let me introduce a differential equation for you. And then I'll finally get back to my larger discussion of Pfaffian forms, which will not be that exciting anyway, so don't worry, you're not missing out too much until I get to it. But here's an example. Solve the differential equation x plus xy squared dx plus y squared plus x squared y dy equals to 0. So solve this differential equation. Is it exact? Right. So what do we do? I mean, you've got P is x plus xy squared. Q is y squared plus x squared y, right? So what does that say partial p partial y is? And what does that say partial q partial x is? Looks like we've got 2xy, yeah? And 2xy, yay! So we meet the exactness condition, right? Well, that's not the exactness, well, okay, yes. We have met this condition. Let me call this the, let's say this is the closed, let's call this the closed condition. Give it a name. Let's call it the closed condition. If you meet that closed condition on a simply connected set, you're good. So this is true on R2, right? R2 is simply connected, by the way. Everything, there's no, you can always deform loops to points that's simply connected. And so yes, we can be sure that there exists f. Now, does that solve the problem for us? No, it does not, right? Right, so we still have to find f. Somebody give this a name because I don't enjoy writing it again. But if you look at star, what is that? It's really differential of what? 1/2 x squared, right? Plus 1/3 y cubed plus 1/2 x squared y squared equals to 0. Where did that come? I mean, we just worked that out at the start of class, right? This is the same math. To find the potential for a conservative vector field is to find the solution to the exact equation in 2 dimensions. In other words, an exact equation, p dx plus q dy, is in fact exact if and only if the corresponding vector field, p comma q, is a conservative vector field. But anyway, there you go. So the solution is what? Thus, 1/2 x squared plus 1/3 y cubed plus 1/2 x squared y squared equals to a constant. Put a box around it. This defines the general implicit solution of star, which was exact, all right? All right. So now I'm going to take a step back and I'm going to do the stuff I usually do at the very start of this course, which is to say, you know, this course is about studying differential equations. We're going to study mostly ordinary differential equations, which means that there's just one independent variable in the problems we're studying, all right? It wouldn't look like it. It looks like there's 2 right now. It's funny. Sorry. But especially as we get past this part of the course, it's clear we're studying ordinary differential equations until the very end, at which point we study partial differential equations. Partial differential equations are important. For example, Maxwell's equations, the equations which govern electric and magnetic fields, those are partial differential equations. Schrodinger's equation is a partial differential equation. The equations at the base of general relativity are partial differential equations. Partial differential equations have more than one independent variable. So like for electricity, electromagnetism, the independent variables would be like space and time. You have partial differential equations involving time derivatives as they relate to space derivatives of the electric and magnetic fields. It's quite a mess, really. In Schrodinger's equation, the independent variables would be like, again, space and time, and the dependent variable would be a complex wave function, all right? So the things we're going to study this semester are necessary to solve those things. When you solve those things, the nuts and bolts of it boils back down to other things we'll learn in this semester. In particular, a lot of times, constant coefficient problems, which was the main topic in the next few weeks. But also sometimes variable coefficient problems. But before all that, we study first-order differential equations. And first-order differential equations are a little bit odd in the sense that we can actually solve nonlinear problems. Past this point, we don't really study nonlinear problems because they're too hard. But in the one-dimensional case, nonlinear problems can be solved by just direct calculus. And so that's what we've actually been working on. So let me just give you a general definition for sort of an arbitrary first-order problem and give you a little bit of terminology, some of which we've already thrown out, all right? So here's the typical first-order ODE. Has the following form. You can write it as dy dx equals to some function, let's say, maybe use h since well, people usually use f, but you should understand that that f has nothing to do with the f I've been talking about up till now. See here, so f of x and y, generally speaking. So you have dy dx, it's equal to some function of x and y. This is a differential equation of first order, all right? There's a theorem which says, there's a theorem we have, and the theorem says that if the partial derivative of this with respect to y is non-zero at a point, and this function is continuous nearby, then there exists a unique solution to this, right? We'll get back to that in a later lecture, but there's some nice theory here that says solutions exist. So what's an explicit, what's an implicit solution? Well, an explicit solution is y equals to, like, let's say phi of x such that what? D phi dx is equal to f of x comma phi of x. In other words, it is a function, right? Well, phi is a function. Phi is a function that when you plug it in and you differentiate it, right? In other words, you put it into the differential equation, it works. That's what an explicit solution is. Explicit is y equals an explicit function of x. What's an implicit solution? And here's a distinction. An implicit solution is perhaps a level curve f of x comma y equals to a constant such that dy dx equals to f of x comma y is a differential consequence of star. And by that I mean you can take the total differential, of the level curve and recover, well, you can recover the Pfaffian form of the given differential equation. What's the Pfaffian form of the differential equation, by the way? That is what I was advertising So this guy has the